If you stare at a massive collection of information long enough, the sheer scale of it turns to noise. Today, we aren't trying to comprehend an entire overwhelming sum of parts. We're looking for one specific, quiet truth buried in the dead center of the chaos. Imagine a tech company is trying to recruit you. To show off how well they treat their staff, they hand you their payroll data, a massive spreadsheet of every single person who works there, from the interns to the executives. The recruiter points to the bottom line of the spreadsheet and makes a very appealing pitch. Our average employee makes $120,000 a year. That single number is mathematically flawless. If you add up all the money the company pays out and divide it by the number of workers, you get exactly $120,000. But relying on that one calculation completely deceives you about the reality of working there. Take a look at this histogram showing the actual distribution of those salaries. Down here on the far left, you have a massive, towering cluster of data points. The vast majority of the workers are making exactly $40,000. Then there's a long, nearly invisible flat line stretching far to the right, ending in a single isolated point. That is the CEO's multi-million-dollar compensation. The mechanical flaw of a mean is it relies on magnitude. Because the formula adds all values together, the sheer weight of the CEO's salary physically pulls the average far away from normal workers. In data science, this phenomenon is called skewed data. It happens anytime asymmetrical extreme outliers distort the center of your distribution. When data is skewed this heavily to one side, the average stops representing the typical experience. Instead, it becomes a metric of the extremes. To fix this, we need a metric that resists the gravity of those extremes. We need the median. Finding the median requires a completely different mechanical process. We have to abandon the sum entirely. Instead, every single data point is organized sequentially, strictly from smallest to largest. Next, we just walk to the exact physical center of that sorted data to find the 50th percentile, or P50. Since this company has exactly 54 employees, our center lands directly between the two center nodes. When you have an even-numbered dataset like this, the rule is to simply average those two middle values to find the exact center point. The median acts as a reliable witness. It ignores the wealth concentrated at the very top and the poverty at the very bottom, reporting only the exact human center of the company. Let's put this to a stress test. Imagine the CEO suddenly gives himself a massive raise, jumping from $2 million to $20 million. Watch how these two metrics react to a sudden, extreme change in the dataset. On the top track, the mean is violently pulled off-screen to the right by the top outlier. But on the bottom track, the median marker stays perfectly locked in place, completely unmoving. The median survived the stress test because it is totally blind to magnitude. It only cares about rank. The CEO's salary got physically much larger, but the median counts it as just one single object. His position in line didn't change. Data scientists use a single line of code to summon this specific metric and bypass extreme noise, simply calling the median function on their data. Relying on positional rank rather than total magnitude is what makes the median bulletproof against outlier interference. This doesn't mean the average is a useless calculation. It just has to be applied to the correct real-world question. If the local government wants to calculate its total tax revenue from the company's employees, the mean is essential. For taxes, the total magnitude of the money is exactly what matters. But if city planners are trying to figure out if a typical worker can actually afford to rent middle-income housing in the area, the median is the only metric that tells the truth. This creates a reliable rule for exploring data. When you need to determine total output, calculate the mean. But when you need to evaluate the typical experience, ask the witness in the middle. Finding that true center point is absolutely crucial, but it is really only the first step in interrogating a dataset. Look at these stacked dot plots. Both share the exact same median and mean, with identical centers. In the top plot, values cluster tightly against the center. In the bottom plot, they scatter wildly across the axis. The spread tells a completely different story. This leaves us with a new problem to solve. How do we mathematically measure the chaos and distance around that center point?
Knowing exactly where the middle lies is meaningless if you don't know how far things spread.